Dr. Saurav Chakrabarti, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today we will be looking at BFS and DFS algorithms and its applications. So, in particular we will be looking at checking for bipartiteness. So, to recap, a graph is given by a set of vertices V1 to Vn and a set of edges E1 to Em. Each edge is a pair of vertices. So, G is given as V comma E. If UV is in the edge E, implies that VU is also in the edge E, then we call that graph as an undirected graph. And weight can be assigned to each of the edges, and in that case the graph is called an weighted graph. So, there are some more basic definitions that we might want to just recap. So, if there is an edge from vertex U to vertex V, we say that V is a neighbor of U. Sometimes we also call it that V is adjacent to U. For an undirected graph, the total number of edges that goes out of U, which is the same as the total number of edges that goes into U, is called the degree of the vertex U. So, for example, here we have a set of vertices, and we represent the set of vertices by some circular nodes in the plane, and the edges, which are a pair of vertices, are represented by a straight line or some curved line also joining those two vertices. For example, here it is an undirected graph. That means this node here indicate that AB is an edge. This node here indicate that BC is an edge. There is no edge here between C and G, means that CG is not an edge in this graph. We can also have weights on these edges. For example, this edge has weight 8 and that edge has weight 7 and so on. In that case, we call it a weighted undirected graph. The other thing is that these edges can be directed. In the other words, denote the direction by an arrow. So, there is an edge from G to E, means G comma E is an edge in this graph. But since there is no arrow from E to G, it means that E comma G is not a edge in this graph. So, in this case it is in the directed setting where G comma is an edge does not imply that E comma G is an edge. We can also denote it by this two-way arrow, which basically means that EC is an edge and CE is an edge in this graph. So, the advantage of studying these graphs are that they help us to mathematically express relationships among objects. This characterization of relationships in terms of graphs is a very simple and general way of doing it. Many real life problems can be formulated as a graph theory problems, and hence studying the graph theory or algorithms for graphs is a very essential object or subject in our field. So, given a graph, one of the most important concepts is connectivity. So, connectivity basically says that whether if we start walking from a vertex to another vertex along the edges, can we reach that vertex. So, we say that for any two vertices U and V is connected if there exists a path from U to V. Note that in an undirected graph, since we have the condition that if uv is an edge, then vu is an edge. So, if there exists a path from u to v, then there also exists a path from v to u. And so, in the case of undirected graph, connectivity is kind of easier. In terms of these graphs, we have also seen that we can have some cycles. So, cycles are say objects like this, like we start walking from G and you go to F, D, B, E and G. So, it is a path that goes from starts from a vertex and reaches back to that vertex without using the same edge more than once. So, one could have also thought of this going from A to D and D to A, but that is not a cycle. A cycle is something that does not use any particular edge more than once. So, this is a cycle, this is also a cycle, a different cycle. So, a graph can have many cycles for that matter. In the case of directed graph, things are a bit more complicated. For example, if you put directions here, so this is not called a cycle, because if you start walking from E, you go to B, then from B you go to A, but from A you cannot go to D because AD is not an edge. So, in the case of directed graphs, we say a cycles has to be a directed path from a vertex to itself without using the same edge more than once. So, let us say this is the one possible cycle going from G to F, F to E and E to G, because this EG edge is 2A. Another important concept is this trees. So, what is a tree? A tree is basically the minimal connected graph one can think of, or in other words, it has lots of other characterizations. For example, a graph that is connected and does not have a cycle is called a tree. A tree also is a graph that is connected and has exactly v minus 1 number of edges. And if a tree touches all the possible vertices, then it is called the spanning tree. So, this characterizations of this tree is something I have not done till now, and I will not be doing it in this lecture also, but these are kind of easy exercises to work out. That fact that if a graph is connected and does not have a cycle, then the graph has exactly v minus 1 edges, and the opposite is also true, that if a graph is connected and has exactly v minus 1 edges, then the graph does not have a cycle. And we also have the condition that every connected graph has a spanning tree. In the case of directed graphs, connectivity is bit more tricky. There we say that u is connected to v if there exists a path from u to v. Directed path from u to v does not imply a directed path from v to u. So, we have to be careful about saying that which is connected to what. A graph that has no directed cycle is called an acyclic graph, and we have also a notion of the connected components, which we can look at later. Now, what are the basic algorithms for graph theory or basic graph algorithms? The basic graph algorithms is the algorithms that traverses the graph or searches the graph, or in other words, it is an algorithm that I give you a graph and ask you that, okay, now take a walk along the edges in such a way that you touch every vertices. It is a very natural concept to ask, correct? It is just like if I give you a graph of the say road network and I ask that, okay, can you go around so that you touch every vertex, or if I want to know whether a particular particular vertex is connected to the rest of the vertices, we want to ask such kind of questions. So, for traversing and searching the graph, we have already seen two algorithms. The first algorithm is called the depth first search, which starts from a vertex v and visits all the reachable vertices in a depth first manner. Means it first looks at one vertex and then adjacent vertex to that and so on till it hits a dead end, comes back and then looks again and so on. We have studied this one couple of lectures ago. Last lecture we also looked at the breadth first search. So, starts from a vertex v and visits all the reachable vertices in a breadth first manner. So, basically starts from a vertex v and first looks at all the neighbors of V. Then it takes one of the neighbors of V and looks at all the neighbors of that vertex and all of them. So, these two are called the basic graph algorithms and they are very crucial. We have seen some examples of that. First of all, both of these algorithms can be used to produce a spanning tree. You recall that both the algorithms finally ends up picking some set of edges and not picking some set of edges. The set of edges picked will give you a spanning tree of the graph or a tree that touches every vertices in the graph, and it does it in a runtime which is linear in the size of the input. The runtime is order V plus E. Note that V plus E is the size of the adjacency list. So, first of all, DFS and BFS are used for finding a spanning tree. It is also important to note that the spanning tree that is achieved by DFS and the spanning tree achieved by BFS are not the same. In fact, a graph can have various different trees or spanning trees, and BFS and DFS just gives one such kind of tree. They also have some other properties, and that is exactly what we are going to look now. So, in the case of the first application, say if we ask the question that given an undirected graph, to check if the graph is connected, again we can run either BFS or DFS. We run and find the spanning tree. While we run it, we will color each of the vertices that we have visited with a particular color, and at the end of the BFS, if there exists some vertex which has not been colored, it means that the graph is not connected. So, this is an application of BFS and DFS to check connectivity. Always keep it on the back of your mind that the runtime for BFS and DFS is order V plus E. So, we are coming up with linear time algorithms for checking connectivity. In the case of directed graph also, if you want to check whether U is connected to V, the same idea works. You start either BFS or DFS from U. So, use U as the root and start, and then if you reach V at some point of time, that will imply that V is connected to U. If you do not reach V, then V is not reachable from U. The idea is that if you start from a vertex, DFS and BFS will make you reach all the reachable vertices from the root. The third application that we have looked at is given a directed undirected graph to check if it has a cycle, and this is exactly a very important problem that we will be looking at today also. Let us take a small break now. After the break, we will come back and look at the problem of finding a cycle. Welcome back after the break. Before the break, we were looking at the problem of given an undirected graph, check if it has a cycle. Again, note that DFS and BFS can be used to check if the graph has a cycle. How? When we were looking at it, note that if the graph has a cycle, then the graph is not a tree, and if graph does not have a cycle, then the graph is a tree. A tree always has only one spanning tree, and that is itself. So, if you run BFS and DFS or DFS on a tree, it would end up picking up all those edges. So, while running DFS and BFS, if I encounter an edge that I need to throw away or I not choose, that implies that the graph has a cycle, because the fact that I will not choose an edge and still manage to produce a spanning tree implies that there must have been a cycle in that graph. What happens in the case of directed graphs? And this is where things become interesting. So, given a directed graph, to check if it has a directed cycle. Till now, all the applications that we gave required us to use either BFS or DFS, either of them would have worked fine. But in this setting, it turns out that it is only the DFS that works, and we have seen the reason of it earlier in our lectures, and it is because of the special DFS structure. as we told, look at this graph and imagine these black edges are the tree edges. Then we have these three different kind of edges. One is the cross edge. Cross edge meaning I look from 6 to 3 when 3 has been completely been looked at. We also have this forward edges, like after doing all of this, finally I come to 1 and I see that, oh, okay, 8 has already been looked at. So, this is a forward edge. Neither of those two indicates that there exists a cycle, but there are edges like back edges which indicate that after I go to 4, it says that there exists a edge back to 2. A back edge implies that there is a path from 2 to 4 and there is a path back to 2. So, thus a back edge implies that there exists directed cycle. So, we can use DFS to find a directed cycle. This same technology or this same algorithm was used for topological sort that we had seen couple of lectures ago. Till now we have looked at connectivity and path. One more important thing is this distance between two vertices. So, we say that the length of a path is the number of edges in the path and the distance of u to v is the length of the shortest path from u to v. For example, consider this graph. Here I have a path which has length 4 because I have used 1, 2, 3, 4 edges. Similarly, I can have a shorter path, say this one, which is a path of length 3. Both of them are directed paths. So, the question is that what is the shortest path, the distance from u to v? This is a problem that we saw last lecture. We can also ask a more general question: what is the shortest distance of any vertex from the vertex v? Again, we saw that doing a BFS is used to find the shortest distance. Note that here only BFS will work, but not DFS. The reason is also because of some structure that BFS follows, and we will be looking at this structure more carefully in the rest of the lecture. We will be looking at the shortest distance much more seriously in a more general setting in the next lecture. One very important concept in this field of graphs is known as the bipartiteness. So, if graph G is called bipartite, if we can write V as a union of two in disjoint sets A union B, such that all the edges are between the vertices of A and vertices of B. Or in other words, there exists no edge between two vertices in A or two vertices in B. If this is the case, we call it two colorable. Recall that we had defined the definition of colorable or K colorable in an earlier lecture. This matches exactly fine with it. So, consider this graph. Now, is this graph bipartite? What we can do is that we can start putting these vertices in the two partitions. Say, without loss of generality, I put A in the partition A. Now, if I put A in the partition A, then I have to put D in the partition B, because I know that there cannot be any edge between two vertices in A. So, I have to put this one in B. Similarly, since this is in A, so I have to put this one in B. Now, since this is in B, I have to put this one in A, because if I put this one in B, then I will have an edge between two vertices in B, which cannot be. So, I have to put this one in A. This is fine, there is the edge between A and B, that is not a problem. But let us see what happens to F. F, because this one is B, I have to put this one A. But if I put this one A, then they will have an edge between two vertices in A. So, this way will not work. So, this is not a bipartite graph. So, here is an example of a graph that cannot be split into two halves. In other words, you can think of A and B are these two sets A and B, and the edges are only between this set of. So, edges like this are not allowed, or edges between here are not allowed. The edges must go only between A and B. For example, say if I just remove this edge EF, then we get a bipartite graph. How? Here I have colored this graph into two colors. you can think of that the blue color goes to A and the red colors goes to B, and note that there exist only edges between vertices of blue color and vertices of red color, and there is no edge between two vertex of blue color or two vertex of red color. This is what makes this concept very interesting, to check whether a graph is bipartite. It turns out that a graph is bipartite if and only if there exists an odd cycle. So, in other words, if I have to prove that a graph is not bipartite, then I have to catch an odd cycle, and if I cannot catch an odd cycle at all, or if there is no odd cycle, then the graph is bipartite. So, this notion seems to be very nice. All we are classifying in terms of whether there exists a odd cycle. So, I mean by odd cycle is a cycle of odd length, and even cycle is a cycle of even length. So, let us try to understand how can we solve this problem. Testing bipartiteness is a very important concept. Bipartiteness gives such a nice structure to graph theory that many algorithms work for bipartite graphs and not for other things, and so on. We might see some more interesting application of bipartiteness later, but it is a very important concept in graph theory. So, in other words, given an undirected graph, if you want to check if it is bipartite, it is same as given an undirected graph, check if it has a odd cycle. So, we do it using breadth first search. So, let us go over the breadth first search algorithm once again. So, remember that in the breadth first search we maintain a queue, and we will indicate the start of the queue with a arrow. We will not remove it, and we start from this vertex h. So, we start from vertex h, we take the wherever the pointer is pointing, and we take all its neighbors and put it in this queue and move the arrow to the next. So, I put h, I put g in the neighbor and move the arrow to the next. Now, G has two neighbors E and F. I put them there and I move the arrow to, I put E and then I put F and I move the arrow to E. Then I take E, I take the first neighbor which is C, then I take the first neighbor which is B, second neighbor, then I take the third neighbor which is D and I move the arrow to F. This is the BFS that we have done. Now, we take F. Now, F has two neighbors, but as soon as we see this F, we see that okay, this E has already been visited, it has been colored blue, and so this edge is not chosen, and similarly the next one D is not chosen. We go to the next one which is C, again same thing, CB is not chosen, then CG is not chosen because both of them are colored. Then I go to B, we look at a neighbor of B which is A, we move to D, and now since DA and DB are both chosen, we do not pick it up, and hence we get the BFS tree, which is the set of the red colors. Remember that in the case of DFS, we had this various tree edge structure. They had 4 different edges. Here also there are various kind of edges, but before that let us look at it. For the pseudocode we had this, we used the NQ and DQ operation on a queue, and using that we had this simple pseudocode operation for this BFS. Note that if at any point of time we get an edge, unfortunately we cannot say that it is a directed edge, that is one thing, but even in an undirected setting, if we get a edge, it just says that it is a cycle, there exists a cycle. We cannot say anything more than there exists a cycle when we discard an edge. So, there are two different kind of edges, the tree edge and the non-tree edge. Now, let us try to understand the non-tree edges slightly better. So, at this time we will keep a track on the distance also. This is something we had done also in the last lecture. We start from h, we put that h as distance 0, and as soon as we see the next set of adjacent its neighbors, we put the distance as just one more than the distance of h. So, we put C and G, and here in the right hand side I am drawing the tree that is growing now. I put C and G, and in both C and G I put the distance as 1 more than what H is. Similarly, I look at now the C and look at the neighbor of C, which is E, and look at C. I look at this neighbor of E, neighbor of C, which is E, and the distance of E is 1 more than its parent, which was C, and since C's neighbor was 1, so I put 2 here. Now, I look at G. At this point, G has 2 edges going out, F and E. Note here that F I write the distance as 2, but this edge E is an edge that is not selected because E is already selected. So, it is non-tree edge. And similarly, for E we do the same thing, we look at these 2 neighbors which are untouched and look at this F, we also see that there is some new edge that is not been there, and so on. Now, one point to note here is that let us look at the graph in the right hand side. In the right hand side, the red edges are the edges that has been selected. Now, what are the edges that are non selected? Note that an edges that are not selected will go. So, I can represent this one as distance 0, this whole string or layer as distance 1, this whole layer as distance 2, and this whole layer as distance 3, and this layer as distance 4. I mean, this is how it is there. Note that the non-tree edges goes from a distance I to I minus 1 or I plus 1 or I. So, I cannot have a non-tree edge going from G to B, because the difference between these two distances 2. The other important thing is to note is that in this graph, if there is a cross edge which goes in the same direction in the same layer, then I get a cycle of this form which is odd, whereas if I get an edge which is in the next layer, I get an even cycle. So, in other words, by looking at the non-tree edges, we can deduce which is whether there is an odd edge, odd cycle or an even cycle. So, if the vertex is at distance k, then it is in layer k, then a non-tree edges must be between 2 consecutive layers, and if there is an edge between 2 vertex of the same layer, we get an odd cycle. So, checking for bipartiteness is just by running the BFS algorithm and checking whether there exists an odd cycle. The runtime is order V plus E. To summarize, we looked at various properties of BFS and DFS, and we saw how to use BFS for checking for bipartiteness. In the next lecture, we will be using BFS for finding out the shortest distance between 2 vertices. So, this we come to the end of the lecture. Thank you.